Any doubt till this point? Any question? So this is basically one, part of the input file. Right. Now let us come to the second part, which is important, which is Monte Carlo moves. So again, the Monte Carlo moves are not fixed. It depends on what type of system you have, what types of ensemble you are using. Right. So for this problem, we have three different types of move. Only the translation move or displacement move. And displacement of what? See, we have a water molecule. So displacement of center of mass. Right. So we have the three atoms, three coordinates, all the masses. Calculate the center of mass. That center of mass will be displaced in a displacement. Right. Then we have the inside this. See, in your input file, you find this term PMTRACM. In your input file, you find where is TRACM. PM is center of mass, TRA is the displacement, or PM is the probability. That one? Yeah, PRTRACM. Inside this TRACM, center of mass translation, right? This is the probability of Monte Carlo moves. We have three parameters. You can check. We have three options are there. We have to fill three options. PM TCMT, RM TRAC, and TA TRAC. Clear? So what is this? This is the probability of performing a center of mass. Random number, you have understood, right? So we are going to make a move based on the random. Right. So what is happening in Monte Carlo? So we have three moves. One is the displacement, then rotation, and finally your volume move. Yes, volume. So see, you have to decide all these moves, which moves you want to apply for your system. Right. So, but almost in each, in each simulation, this displacement rotation will be there. But if you are doing it NVT, volume is constant. So this volume move is not required because the volume is constant. Right? Yeah. Okay. Now see what is done is we generate a random number. So random number is any number between 0 and 1. Any number between 0 and 1. Right. So what we are doing is, so you just check your input file. So here we have PM ball. Is for the volume move. So in your input file, you have a variable with the name of PM ball. So this is the volume move. PM TRACM, displacement move, and then rotation move. So for this particular problem, we have three moves. Right. And under each move, we have one number. 0.1, 0.7, and 1. Right. So what is the meaning is, if you are generating a random number, and if random number is less than 0.1, if random number is less than 0.1, random number is less than 0.1, then perform the volume move. So this is the meaning. So we have three moves. we have to make move based on randomness probability. So generate a random number. If random number is below 0.1, less than equal to 0.1, from 0 to 0.1, perform the volume move. Okay. We will discuss. See, there is two options. For your system, you read the literature, find the values. If you don't know, you give some number. Final result is not dependent on all these numbers. Optimum number will help you to achieve the equilibrium state fast. If you are giving an optimum number, so you will achieve the equilibrium state fast. Otherwise, it will take some time. So your final result is independent of all these moves of probability moves. So normally there is thumb rules. Thumb rules is most of the time we have 100%. So out of 100%, we have to decide how much we have to give to the displacement move. Right. So the maximum weightage we give to the displacement. Let's say max 1. So out of 100%, give a maximum weightage to the displacement move. So that molecules are moving inside the system most of the time, right? Then give the second weightage to the rotation move, and finally is the volume move. So generally, we do not perform volume move, more than 10%. Out of 100, maximum, we give the probability to the volume move is 10%. So that's why we have 0.1. So this is probability. 0.1 is 10%. So maximum is 100%. Clear? Meaning of this thing is clear. So we are going to generate a random number, right? So if the random number is less than equal to 0.1, we will have a volume move. Right? Now, if the random number is greater than 0.1, if the random number is less than equal to 0.7 and greater than 0.1, then perform the second move, which is the translation move or displacement. Clear? So the number means 0.7 means if the random number is greater than this and less than this number, so it will perform the displacement or translation. Now the third is if the random number is greater than 0.7 and less than equal to 1, then perform the rotation. So all these probabilities are cumulative. So ultimately at the last it has to be 1. If let's say you are doing another problem where you have another move. So similarly, you have to put another variable, right? Then you have to decide how much weightage you want to give to the. See, in this case, we are giving 60% weightage to the translation move. 60% of the time we are going to do the translation move, then 30% rotation, then 10% volume. So that's what I'm saying. So maximum time we give weightage to the displacement, then rotation, then volume. Move is less than 10%. Any question in these moves? So as per your problem, depending on type of system, depending on what type of ensemble you are using, so additional moves you have to have, and then again you have to decide the weightage. So this is important. But your final result is independent of all these weightages. Final result is independent. In each case, you will get the same final result. Only if you're giving the optimum numbers, you will get the equilibrium state. Okay. Now inside, see, right now we have given only the probability of each move. Inside each move, we have three options, three variables. We have three options. So first is the PM, VR, PR. So PM is basically the variable which represents that we are making a move, Monte Carlo. So PM is common. Right. So here is PR is probability. So what is the probability of doing the volume move? It means if your number is less than 0.1, so it is sure. So one means that it is sure that we have to perform the volume move. One means probability is 1. It means if you have already selected the volume move, then one means you have to perform the volume move. Right. So we will discuss on these variables again in the two-box simulation. When we have the two-box simulation or more than one molecules, right? Then we will discuss this. But in this case, we have only one simulation box, one molecule. Right. So when we have selected the volume move, so we have only one box. So you have to perform the move. If you have, let's say, two boxes, so randomly we can select any one box. We will discuss those things in another example. Clear? Then what is this RM wall? We have discussed, right? Rotation, yes. We have talked about the maximum displacement. So maximum displacement, some number has to be given, but as the simulation progresses, this will be achieved some number, fixed number. So you have to provide the maximum center of mass displacement in angstrom. It means in a particular move, maximum how distance, how much distance a molecule can move. Center of mass of the molecule can move. So again, if you do not know what is the optimum, you put some number. Why? Because the last option is set is basically target acceptance rate. Right. So this is a target acceptance rate. So number is between 0 to 1, but typically we put in the range of 0.3 to 0.5. We have already discussed that if the acceptance rate is high, this number will be changed during the course of the simulation. So in each simulation, you do not have to change this number. This will be constant, whatever simulation you are doing. This is the maximum volume delta V max, right? And this is the target. So target by default is 50%. Again, in case of displacement, maximum delta X max is 0.5 angstrom or target is 50%. Again, in rotation, maximum is 0.05, target is 0. All your simulations, these two variables will remain same. Only thing that will change is this first number. We have multi-component and multi-box, then this number will change. In pure component, this will be same. And again, you have to change all these numbers. So in this case, you put all these numbers and remove all the other things in the input file. So we have so many variables. So remove all the variables. Only you keep volume, translation, and rotation. So this target acceptance is, again based on literature. Typically, it ranges from 0.3 to 0.5. If you do not have any information, keep it 0.5. So remove all the other options from the input file. You can just put it 0. Remove it. Remove everything. Only keep these three variables. Only three. Are you going to do it? Yes. Yes. I already have the input file.
PM throttle. You have to come to this level that will remove all other options.
Remove everything else, whatever is there in the input. Because this is a default input file, so other options are there. Remove digital. No, they have to only change in the your text file. All the changes has to be done in the text file only.
Yeah, I know, but many.
Open the text file and do the changes.
Okay, bring it in the text file. Bring it in this environment. Yeah, editor, you have to open that.
If you are making 100 books, but say except only 50. See, these moves are important because the Monte Carlo simulation is based on moves. We are not following any equations, standard equations. So for your system, you have to identify the moves. Then you give some number to moves based on literature value, or otherwise you follow this thing: displacement, rotation, then volume. You will see all other examples. Yes. Rotate is 0.05.
No, sir, not. The description where EMROMT.
Oh, description. Okay.
One.
See, all things are available in the your manual.
This.
See, you just check okay, where is the. I'm not given the links, but I will send you the links and all the information. Because I'm only showing the 3 moves. In the input file, there are more than 10 or 15 moves. I will send the link. So, any question in the move? Rotation, and volume. These are the 3 moves. For the time being, you can ignore these 3 variables right now. Keep as it is. When we'll do the multi-component simulation, multi-boxes, then we will change these values. Then you will clearly understand the meaning. Single component, single box. Okay. Done. Okay, now go to see, remove all the other things. Whatever is there, remove. Now go to the next. You find CBMC formulation. We have discussed, CBMC. This is an algorithm for building the molecule. From the information, we will give the information. This is one algorithm, and this is the name of the algorithm. This was developed in 99 plus 2004. What is it there? You pick as it is. Done. Then you check CBMC setting style. If it has default ideal, you don't change. So if you understand algorithm, then only you can do the changes. If you do not understand, keep the default like it. Later on, you can explore all different algorithms. And in the start, you keep the default. Once you know how to run the simulation, how to do the analysis, then you can go back in the algorithm part. So these two will be same. So now we are discussing the third part. So first part we have done before the lunch. Second part is moves. Then this is the third part. Okay, so next is the FF number, force field files. How many force field files are required? So in this case, we have only water molecule, and we are going to make one force field file for water molecule. Right now, let's say you have 10 molecules. So you have two options. You make one force field file and put all the information in that folder, in that file, or you make 10 different files, one for each one. Okay. So this is the number about the how many force field file is available with us. None. Then this is the file location. Now you change the file location as per your folder. Currently you are doing making input file at some folder location, right? Now you change the location in a similar fashion. We are going to make the force field file. So right now you just put the folder location. See, open your CMD, and go to your folder. Open CMD, go to your folder. Then you type PWD, project working directory. So it will print some information. Go to your folder and type PWD, present working directory. It will print some information. That is your folder location file, total address. Present working directory. Select the one in the white button. You just select at the top, do the right click. Can I just file location. File location. But when you will run the simulation, माउंट लिखना पड़ेगा क्या? नहीं, ई से लिखना पड़ेगा ना?
So go to your folder where you made PC something like that or tutorial. There you have to write PWD.
माउंट पूरा लिखना पड़ेगा?
नहीं वो एक्चुअली माउंट के अंदर ही है.
हाँ, जैसे हमारे केस में क्या है, हमने जब करा था तो लिनक्स डाला था तो स्टार्टिंग होता है होम से. इस केस में कहाँ से होगा?
इसलिए आप अगर पाथ नहीं देंगे तो बाय डिफॉल्ट इंस्टॉल किया है विंडोज एमएनटी पे तो ट्राई जाता है.
तो मिलेगा नहीं तो एरर आ जाएगा.
That is I am showing you.
So let them put maybe whole address, then we will check. ना पता नहीं माउंट में क्या है, इसको देखना पड़ेगा.
हाँ, वो क्या है? PWD अलग से CMD खोल के कर रहा है. तो
हाँ ठीक है, दिखा दिया ना, ठीक है. You follow these steps. You follow these steps. Go to the Tahi folder.
Now,
Then first you have to go to the Tahi folder and go to the folder where your Tahi underscore input file. Then you type PWD. It will print this information. चेक करते हैं, रन करके पता चलेगा कि माउंट लगेगा कि नहीं लगेगा. I can change it also. Yes, what?
This one.
We can do this part later on also because we have not yet made the force field file. Yeah? So we will make the force field file, then you can enter the address. We have to give the address of the force field file location. करते हैं वो रन करेंगे फिर देखेंगे. Can do this, this part later also. And this is the name of the force field file. So this is the format which Tohi follows. Tohi underscore FF underscore the name of the force field. So in this case, we are using one model for water which is known as the SPCE. We will discuss what is SPCE. We will discuss. So you can leave this also, right? No, if you have entered, then it's okay. Later on, we can enter also. Okay, next is the classical underscore potential. And we have already discussed Lennard-Jones. We are going to calculate the interaction between the atoms which are not connected through the Lennard-Jones potential. Lennard-Jones potential is 4 epsilon, then sigma by r to the power 12 minus sigma by r to the power 6. So that is the functional form of the Lennard-Jones. We are going to calculate the energy using that. Clear? Then classical mix rule. See, what is the meaning of classical mix rule is we have say different atoms, hydrogen and oxygen. Right now, for each atom, I will show you the force field file. We need some information. Let's say we need some information. Also, what are the parameters? Right. So when we have, when we are calculating the interaction between, let's say, oxygen and hydrogen, both are different atoms. Right. In the equation, we need sigma and epsilon when we are calculating the interaction between oxygen and hydrogen. Right now. So the how to calculate? So calculate the geometric mean. For each atom, we have sigma epsilon. I will show you what is sigma epsilon. Right? If the atoms are different, for sigma, you calculate the geometric mean. So geometric means is the square root of sigma 1, sigma 2. So we know sigma 1, we know sigma 2. So for the combination, you use geometric mean. Similarly, for epsilon, use epsilon 1, epsilon 2 square. So it will be, almost constant in each simulation. We are going to always use almost every time we will be using the Lennard-Jones potential. And for mixing rule, geometric, we have two options. One is the geometric, another is the arithmetic. In arithmetic, sigma will be sigma 1 plus sigma 2 by 2. Right now. Any question? We are going to use Lennard-Jones, and if the atoms are different, use the geometric mean to calculate these two variables. We will discuss about these variables when we make the this force field file. So you can make the changes in your input file. Okay. See, these variables are important, huh? So we have to understand. After this, we have L shift. We have L shift. What is the meaning is So this is a logical variable. So it will take either true or false. So true means non-bonded potential is shifted so that it is zero at the cutoff. We are calculating the interaction between the two atoms. See, in the last lecture also the sir has discussed. We are doing the simulation for calculating the interactions. We are cutting the system. We are not calculating the interactions beyond a certain distance. Right now. So let's say this is a box. Let's say 30 angstrom. So we have to give the information about our cutoff length. Till this point, you calculate the interaction between the atoms. After that, interaction is zero. So if let's say we have oxygen atom and hydrogen atom, we are doing the calculation. So here is the oxygen at the center. So this is a circle of let's say 10 angstrom. Right now. So when you are going to calculate the let's say Lennard-Jones potential, 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6. So this is the non-bonded interaction known as Lennard-Jones potential. Right now. So we have to calculate this between two atoms which are not connected. Right. So we need distance. Right. So we are telling the software that don't consider a distance beyond 10 angstrom. It means if r is greater than 10, so this potential will be zero. This potential is zero. If distance is less than r, then only you use this equation. Yeah. Why? Because if you plot in the last lecture, I also discussed. If you plot, this r versus potential, right? So you will get a curve, something like this. So practically, if you will see after 10 angstrom to 12 angstrom, so this is close to zero. So that's why we are saying, so don't do the calculation after 10 angstrom. So this 10 angstrom is not a default value. You have to decide. Normally 10, 12, 14 angstrom we take for the cut. Right. So here is our R cut. R cut. So R cut is the distance beyond which the non-bonded potential are no longer computed. After this distance, don't do this calculation. Only do your calculation for this LJ potential if the distance is less than 10. Right now. Any question here? Example, how to put this one right now. So for the time being, you just understand we need a cutoff. Beyond that, we are not going to do this calculation. For your case, let's say this is 10 angstrom. Okay. So this is done. Now let us come to the L shift. Now we have two options. This option says a non-bonded potential is shifted. See, after 10 angstrom, we have some value. We are ignoring that value. So we have two options that you shift this function in such a way that this is zero at the cutoff. Right? This is one option. Second option is L tail C. This is tail correction. Apply the tail correction for the portion of the potential that is past the cutoff. So we have two options. Either you change your potential function in such a fashion that the potential is zero at the cutoff, or you do the calculation till cutoff, and after that you apply the tail corrections to calculate those interactions which are beyond the cutoff. Okay. So in this case, normally we use this tail correction. In the code, you have two options. Either you do the shifting or you do the tail correction. So maximum time we do the tail correction. So that's why this shifting is false and tail correction is true. This is the meaning. And in its simulation, this will be constant. So any question on this, tail correction and shifting? Use tail correction. So if you want to use Fourier system, then use shift correction. Don't do the tail correction. See, tail correction is basically empirical relation. So you can easily calculate, this tail correction. Otherwise, it will modify your LJ potential, and then it will do all the calculations. So this tail correction is basically there is one empirical equation. It will only calculate those. So L shift is okay. Tail correction is done. Then we have R mean. R mean means minimum R, minimum radius, right now. So you can read this should be set smaller than the smallest radius of any atom. Van der Waals equation, we are doing the calculation till cutoff. After that, whatever contribution is there, we are putting in the tail cutoff. So this variable is clear. It should be smaller than any atom. So by default, it is 1 angstrom. So you do not have to change this line. Take R mean is equal to 1 angstrom. R cut we have already discussed right now, and this R cut in. So the meaning of these two variables are same. This is done here, right now, and this is done in CBMC. This is used in CBMC. So typically we keep these two values same. R cut or R cut in. Typically the same values, but both are used in two different, for different purposes. So you make all the changes in your input file. Done. R cut in. Now this is a variable which is generally kept similar to your R cut, and where it is used? It is used in the CBMC moves. CBMC we have discussed. This is an algorithm for the development of molecules from the given information. Okay, next. So see, all this information is for the LJ potential calculation. Right now, similarly, we have to give information regarding the Coulombic calculation. All the atom has charges, right? So there will be, they will apply the Coulomb's law to calculate the interactions, right? So this is the variable electrostatic underscore form. So we are using Coulomb's law. And how this calculation is done? So there is one algorithm which is known as the evolved. So this is the name of the algorithm to calculate the electrostatic interaction. So evolved some parameters. This is one algorithm using which we do the electrostatic calculation. And these are the parameters. These three are the parameters which are used in this algorithm. Keep it default values. Because you have to understand all the meanings. You do not understand, you keep the default. You will get some data. So in almost all your simulations, all 2 plus 3, 5 will be constant. We are not going to change this information. We are going to do the Coulombic interaction calculation using the evolved summation algorithm using some parameters. Similarly, for LJ calculations, we are always, LJ calculation starts from here. Classic potential is Lennard-Jones, then geometric mix rule. Else if false, tail correction apply, then cutoff. Only thing that will change is this R cut and R cutting. Others will remain same. We will see in different examples. We will see how to put this cutoff. Yes, now this is the last part of your input file. So we have basically four sections, 3 and 4. Moves was the second, and then algebra calculation with electrostatic is the third, and this is the final one. How to construct a molecule toy. So far we have not yet constructed the molecule. We have to fail the simulation. That we are going to use the water molecule. And the last part will be the force field find. What are the different parameters? Right. So this part is important. Your whole simulation will depend on how you define the molecule. See, in the TOEI, we have how many options? 3 plus 3, 6 options are there to construct the molecule. To construct the molecule, we have 3 options. So if you are using proteins, DNA, carbon nanotubes, then you have to use all the 3 options. For normal molecules, organic molecules, we generally use 1, 2, first top 2. Basic connectivity map or advanced connectivity map. Both are 90 to 95% similar. Both are similar. And these are the spatial types. Your DNA, proteins, and carbon. So we will discuss how to make the molecule using the basic connectivity. So in your input file, you check this variable input underscore style and remove other things. If extra information is there, you remove. So molecule, it starts with this variable input underscore style. So here we are using basic connectivity map. Done. Now in this case, we have water. So you have to tell how many atoms are there. Right. The second variable is an unit, the number of atoms in one molecule. So we have 3. Then second is n max CBMC. Again, it will be using CBMC, right now. So keep this equal to this. N max CBMC 3. This is not required. PDB names is false. This is not required, so false. This is the name of the force field. This is the name of the force field. Name is SPC-E. We will see what is SPC. So similarly, for your molecule, there will be some name. This name is not standard. You can give any name. Whatever name you want to give, put some variable. But throughout your input file, you have to use the same. Then we have the charge assignment. In this case, we have 3 atoms. All the atoms have some charges. So we are going to put all the charge information manually. The information about the charges on each atom manually. Again, this is a simple thing. What is the connectivity map? How many atoms are there? What is the name of the force field and charge assignment is fine. So make the changes in your input file and remove other things. Now this is important. So here we are defining the molecule. So this is our molecule, HOH. See, in this water, we have 3 atoms. 1 oxygen atom and 2 hydrogen atom. Right. But in simulation, we have to tell how many different types of atoms are there. Total 3 atoms, but type is 2. Right? One is the oxygen, another is the hydrogen. Right? Similarly, now suppose you have this molecule. Now tell me how many types of atoms are there? How many types of atoms are there? See. Here we have one carbon, right now. So let's put one carbon. And all these 3 atoms are connected with the same carbon. So all these 3 are of the same nature. Chemically same nature, right? So this is 2. This carbon is different from this carbon. So it is connected with the oxygen. So this will be 3. These 2 hydrogen are connected with the same carbon. So will be of the same nature. So this is 4. Then we have the oxygen 5. This hydrogen is different from all these hydrogens. So we have. So this is the meaning of this type. So for your molecule, you have to identify what are the different types of atoms are present. So in this case, we have only 2 types, but total 3 atoms. So the first is unit and type. QQ atom is the charge. QQ atom variable means charge. So first line will be unit and type QQ atom. See, also give numbering. Put a number. So let's say this is 1, 2, and 3. So for each simulation, draw the structure of your molecule, put the numbers and types. Now the first is unit is 1. Unit 1 means this hydrogen. And what is the type? So I am defining a type HW. So again, this will be defined by you. You will define what variable you want to assign that type. So I am saying the first unit is, we are starting with first, and the type is HW, and this is the charge on the hydrogen atom, 0.423. So this is the meaning of this line. Simple. Now second is vibration. So vibration meaning is this atom 1 is connected with how many atoms? So this atom 1 is connected with only 1 atom. So write 1. Second line tells this one. The first line under the vibration heading is the number of atoms that are bonded to the current atom. So we are talking about atom number 1, and this is bonded with 1. So we have written 1. Done. Now this line says what is the number of the atom with which this 1 is connected. So 1 is connected with the atom having number 2. We always start with the atom number. So we are starting with atom number 1. We have defined atom 1, type and charge. Now vibration first is with how many atoms this atom 1 is connected? 1, which is oxygen. And what is the number? So number is 2. Done. Number 1 is what is the total number of atoms with which this HW is connected? 1. And what is the number of that 1? That type 2, because we are giving the number 1, 2, 3. Second line, and see in this case we do not have an improper, so this is 0. We have bond, angle, dihedral. Dihedral, you understand, right? Bond, angle, dihedral. So in this case we do not have a dihedral. We will discuss another example. Then I will show you how to write this information. In this case it is 0. Now from second it will be clear. So first is over. Now go to the second. So second is 2. Type is OW. This is the charge. Now vibration. Now O2 is connected with how many atoms? 2. So we have written 2. And what are those two? 1 and 3. So we have written 1 space 3. Similarly, you complete the third one. Third one is HW, charge is given, connected with what one atom, the name, the number is 2. So this is how we define the atoms in the top. This is a simple. Which number? Number of the atoms which we have given. Yes, it will be. Yes, we will take another example of ethanol. So in that case, this this definition will be completely different. So first complete this one, then we will make this ethanol example. In ethanol, we have a dihedral, so we have to give information about the dihedral. So this is the format you have to define properly this format. So any question? To make all the changes in your input file and remove everything else. So whatever we have not discussed, remove all those parts. Which style? Yes. So we are using basic connectivity map, one of the simplest type. So we can easily draw the molecule, put the numbers, types we know. So simply look from 1 to 6. No. This one. Any question from here? For complex, we will do another example. For water, okay, see, when we are doing the simulation, let's say we have ethanol. In ethanol, we have a hydrogen. Here also we have a hydrogen. So we have to make a difference between all the hydrogens. The meaning is hydrogen also. This is user defined. But if you are defining the same thing, then it will come to. What? So input file is complete. Right now, input file is complete. Numbers. You can check. Oh. So you will retake all the values. If you have any doubt, you can discuss. So we started with ensemble, temperature for pressure, molecule type, number, boxes, cycle. Step in all the print frequency. Then limit is true. Dimensions, full CBMC, simple cubic, box sizes, all the probabilities, right? Then LJ potential, Coulombic, all cutoffs, and in last we have molecule definition. So this is your input file. Sir, why is the what we need pura? Improper is what? Using 3 atoms, we make 1 plane. Suppose we have 4 atoms. Take 3 atoms, we make a plane. Right? Similarly, you take another 3 atoms, make it in the angle between 2 planes. The angle means angle between 2 planes. Taking 3 atoms at a time. In another example, we will see dihedral. See, for this example, you only consider what we have discussed because we have several other examples. This is the simplest one. If you have any question and or any doubt in this file, you can. By default, take one. See, if you want to do simple specialized simulation in some solvent, when you do the dielectric constant of the solvent, then you can put. Simulation, if we print all the output, so full means print all the integrations.
Is file accordingly.
Please make the input file correctly, then only your simulation will run. Okay. This is the input file. So we need two files. One is the Tohi underscore input, and second is the Tohi underscore FF underscore dash dash. That is your force field file. Now we are going to make the force field file. And this is important. So we have to make this force field file each time for your molecule. So this is the information for water, and see these are the parameters, right? So for see water has a different models. But in this case, the model is SPCE water model. So this is the SPCE water model where we have three different atoms. This is the sigma. We have written somewhere the sigma. So sigma is the you can think of sigma as a diameter. Each atom has some diameter. So sigma of oxygen. So this is 3.166 angstrom. So for each molecule, you have to find this information from the literature. For your molecule, you have to do the literature search, find this thing. For the standard one, like water, this is given. This is available. Then, so see, for oxygen, for each atom, we need sigma and epsilon. Sigma and epsilon. So I have constructed one graph. So this was the graph. So this base is basically sigma. Epsilon. Epsilon. So we need sigma and epsilon, and these are the units. Units are important. All the units are important. So this is in kilocalorie per mole. In this force field, hydrogen doesn't have a sigma and epsilon. This is 0. In SPCE water model, only oxygen has sigma and epsilon, but hydrogen doesn't. In different models, we can have a sigma and epsilon value for hydrogen. Right? This is the charge on the oxygen atom. This is the charge on the hydrogen atom. This is the bond length. So in this case, We have this bond, so the length is 1 angstrom. In different force field, we have different lengths. Similarly, the angle. Right. So this bond length and angle is required to calculate the bond energy and angle energy. We have written one equation. So we are going to calculate bond energy by equations K R minus R naught whole square. Right now. So here is one constant, and this is the equilibrium distance R naught. So this 1 angstrom is your equilibrium distance, and this R will vary. How the molecules are moving inside the box. But in this case, in SPCE model, we do not have a K. It means the bond length is fixed. In any model, we do not have information about this K constant. It means the bond length is fixed. During the simulation, bond length will remain constant at 1 angstrom. Similarly, during the simulation, similar to this, we have U theta. U theta is K theta R minus R theta square. So this is the equilibrium angle, not R. It is theta. Theta minus theta naught. Equilibrium angle. And this is the equilibrium constant. So we need information about this K theta and theta naught. But in the SPCE model, this angle is also constant. Done? So this is the information required to develop the force field. So you can note down all these values. And the units are important. Degree, angstrom, charge is okay, kilocalorie per mole, and angstrom. In different places, yes, you will find different units of epsilon. Somewhere in kilojoule or some other unit. So you have to collect, from literature, the force field parameter information. Then only you can construct the force field. Okay. Now let us go. Yes. See, go to your TOHI folder. Yes, this is your TOHI folder. In the TOHI folder, there is one folder force field. Click on the force field. Right. So here we have different force fields available inside the TOHI. Right. So you copy. Where is water? Yes. So here you have TOHI underscore FF underscore SPCE. So you copy this one and paste in your folder wherever you are doing the work. TOHI this is the format. You cannot change this format. TOHI underscore FF underscore then some variable. Right. See everywhere this is TOHI underscore FF is common. Only thing changing is the last one, which is basically the name of the force field. All these have the name of the force. So copy and paste SPCE. Now you open your force field file. We need to file TOHI underscore input is the first we have completed. Now come to this force field file. No. Now let us go one by one. See, the first is TOHI underscore FF version. So this is the name version of the force field file. What version it is showing? 15. So right now it is 15. Right. Now the main thing starts from here. Right now. So in the force field file, how many informations are required? We require informations on the non-bonded types. Non-bonded types is sigma epsilon. Then bond, then angle, then dihedral. So we have to give information about the four things: non-bonded, bonded, angle, direction. So we will always start with the non-bonded. So first you have to write at the top is what is the number of non-bonded types. Non-bonded types. So in this case, how many atom types we have? Two, HW and OW. So you write two. The force field file will change every time with a new molecule. If you're using the same molecule every time, same little time. So this is very easy. And what type of potential we are using? So we are using Lennard-Jones potential. So this will remain same. And what type of mixing rule we are using? So we have defined geometric. Huh? So you write geometric. So this is another mixing rule, which is known as the LB. So you write geometric. You remove everything. You write geometric. You make all the changes in your input file, in your force field file. So this will be 15, 2, Lennard-Jones, and geometry. So right now, the first is we have to put all the information regarding non-bonded type atoms. Done. Now go to the next. So we have two. So we will start with one atom type number. We have two atom types. So first is first. So we start with one. Done. Then non-bonded coefficients. So we need sigma and epsilon. So first line will be sigma. This format is fixed. First line is always your sigma, and the unit is angstrom. So in your case, the sigma is given as 3.166. 3.166. 1655, the same thing. But in the Tauhi, this epsilon has a unit of Kelvin. Epsilon has a unit of Kelvin. But the information available is kilocalorie per mole. Right now. So now you convert this kilocalorie per mole into Kelvin and check your values. Check karo. So for non-bonded coefficients, see, for non-bonded coefficients, four variables are defined. In your file, you can find 4 lines. Right now, but we are going to use only 2 lines. These 2 lines we are not going to use in the LJ potential type. In LJ potential, we need only sigma epsilon. The remaining will be 0. The first will be sigma, second will be epsilon. So this is the format. So you cannot remove these 2 lines. There will be 4 lines total. Last 2 will be 0. Only change the first 2 lines. So convert your kilocalorie per mole into Kelvin and put that value. You are going to change this kilocalorie per mole into Kelvin. The kilocalorie is the kilocalorie. 0.155. 0.15535. So this is kilocalorie per mole. You have to convert this into Kelvin. Convert this into Kelvin. Yes. See, this Kelvin is not a unit of temperature. In simulation, Kelvin is a unit for energy. No, not temperature. See, we have what the KB Boltzmann constant, right? So Boltzmann constant is 1.3. 328 into 10 to the power minus 23 joule, yeah, per Kelvin. Joule per Kelvin. KB, Boltzmann constant. Check the unit. Joule per Kelvin. And this is, and here also, this is for one molecule. Molecule is here. So convert this kilo. See, here we have joule right now. So convert this kilocalorie into joule. So 0.15535 into 1000. This is calorie. Then we have 4.182 joule. So we have converted kilocalorie into joule. Then divide divided by Avogadro number, 6.022 into 10 to the power 23. So the unit is joule per molecule. So we have converted kilocalorie mole into joule per molecule. Kilocalorie convert into joule, then divided by Avogadro number. So this is joule per molecule. Right now, then you divide this whatever you are getting by KB Boltzmann constant, which is joule per Kelvin. So joule and joule will be cancelled out. So you will be. You have to do the unit conversion in this case. So if you do the conversion, you will get a value of 78.196 Kelvin. So this is the unit of energy. Unit of. Right. So for first atom, right, we have a non-bonded coefficient of these two. Remaining two will be blank. And what is that atom? Oxygen. So mass is 16. What is the element? Oxygen. So you have to put all the information. Then what is the bond pattern? sp3. See, if you know the bond pattern, you put it. Otherwise, you put null. It will try to figure out based on the information whatever we have given in the input file about the molecule. If you know, put sp3. Otherwise, null or what? You will see. Right now, just put sp3. Then base charge 0. This is by default one. We do not have to change all these things. Base charge 0 and this polarity. Keep as it is. Important is put the number, put these two numbers, mass, element. Done. Then what is the name of the force field? Now this has to be matched with the variable which we have defined in the input file. In the input file, when we have defined the molecule, so at the top we have written force field name. So this has to be matched with. Then atom names. Then atom names. For atom names, we have 4 variables. Right now. So you can, we have already got OW. So write OW. If you want to change, option is there. If you want to change, you can give a different variable to the bonded, right? So this represents non-bonded, bonded angle diagram. If you want to give another variable for this, you can. Normally, we keep only one variable for one atom type. The atom type for OW, oxygen OW. So you put OW. Now this has to be repeated for each type of atoms. So this is for the atom one only, right? Now you repeat this for the hydrogen atom. So you just check your hydrogen atom. So any question from you? So all are compulsory. Whatever we have written, all are compulsory. Now you do the same in the input file. You already have the information. Second is, hydrogen. So we have 0, all zeros. Mass is 1, element is hydrogen, bond is S. This is, and here we have SPC and the name is HW. Similarly, if in your system there are 10 atoms, so you have to repeat this format 10 times for each atom type. Any question? Okay. You take your Chohi underscore input at the bottom. When we have defined the molecule, so we have written force field. So that variable has to be matched with this same variable. We have to use all the time.
Force field OPLS.
What is written?
OPLS.
Change this. Change it. Right, SPCE. SPCE. So this is user dependent, right? This is not universal. So whatever variable you want to give, you put the name of the variable, but the same variable has to be used where we have force field name. Same variable. So this is about non-bonded. Similarly, the second line will be what? Bonded. So bonded, the same thing. Number of bonded terms. How many terms? One. OH. OH. How many bond type number? Only one. We will discuss bond style, right? So bond coefficients 1. Bond length is fixed 1 angstrom. You just read and then tell me where is the doubt. In your force field file, you check all these values. Now see, if the number of bonded terms are 10, right now, then you have to repeat from here to here 10 times. 1, then 2, 3, 4, 5, 10. This is this we will discuss. What is bond style? We will see. Under the bond coefficients, we need two informations. But in this case, bond length is fixed. So this is 1 angstrom. This is 1 angstrom. Vibration order, we don't know. So put while. It will guess. The CBMC algorithm will guess. This is the name of the force field. Number of atoms with the same parameters 1. And what are the two different atoms? OW and HW. So we are defining the bond length parameters for OW and HW. Done. And the final is angle. So how many angle terms? 1 HOH. Number is 1. Style we will discuss. And these two are the coefficients. The first one is the angle. And second one is the K theta. K theta. In this case, see, we do not have a K theta value. We want to fix the angle. So we use a very less value of K theta. So it keeps the angle fixed. Okay. In the angle coefficients, we need two information. So first is the theta naught. Second is the K theta. So theta naught is 109.47 angstrom. In this case, this K theta value is not given. So we are taking a very less value, 10 to the power -4 or -5. If you want to fix the angle, use this one. Then other thing are saying while SPC number of atoms, what are the atoms? So HW, OW is 2. Done. And all the remaining are 0. So we do not have a torsion, improper angle, this all this term. So make everything 0. Now let us discuss two things which is important. What are the bond styles? For bond style, we are using a number. So in the manual, bond style means what? Equations. Equations. So these are the equations. We are using one fixed bond length. In another example, when we are going to solve the ethanol, so we are going to use two simple, standard harmonic, right? Standard harmonic. So this is the vibration coefficient 0. So this will be the first line. 1 is second line. So 0 is for the first line, 1 is for the second line. So these are the different styles which are available in the your program. So most of the time we will be using standard harmonic. But in this particular case, water, we have a fixed bond length, so it is. Right? So in this case, keep it 1. Similarly, for angle style, we are using 1. What is the meaning of 1? So 1 is standard harmonic, or you can also use 0 rigid angle. You can run the simulations by using 2 different options. You only use 0, then put the angle, run the simulation. You put 1, it's standard harmonic. Right, so we need 2 coefficients, 0 and 1. So 0 is what? Theta minus theta naught. So theta naught is the first line, second line is the k theta, which is this constant. Any question for me? See, all these are important. Huh? We have to decide what is the form of the equations, what constants are there, what is the unit of the constant, what is the unit of the constant. That is also important. And in which line we have to put which constant. In some of the another equations, you may have several constants 0, 1, 2, 3, 4. So first line is 0, then 1, 2, 3. So this is done. So now we have the 2 files. Trolley underscore input, and second file is the trolley underscore post. Done. Now in the input file, you put the correct path of the force fields. Now you run the simulation. The force field file. So complete everything, then you have to run. For run, we have a simple command, right? So in the folder, you have 2 files, input and force field, right now. Then you just type. So this is the simple command to run. And you have to do one more thing. Go to your folder. Where is the force field? Yes. Go to your folder. Go to the source. From the source, you copy this file. Executable. This is the executable. 5312 KB. So copy this one and put in the same folder. Now you need Tohi underscore input, Tohi underscore FF, and this one Tohi. So this is available in source. So in one folder, we have 3 things. Now you run this command and check. So you will get errors. मुंह से आता था इसलिए मुंह से नहीं आ रहा अच्छा हाँ देखो क्या where to see the density? Density, yes. Now going to our section, right? Now it is pre-packed soil foundation. On the different transported you can find क्या हो रहा है एरर ओपनिंग फाइल ये फाइल डॉट सही ही डालना ये तो क्या फॉर्मेशन डालना डॉट डॉट उस डॉट का दिखाओ क्या हो तुम्हारा मोस्ट एरर ओपनिंग फाइल दिस input file data our this dot location it class name of this file this one ये टावरिंग क्लास में ये चीज
Vibration because different person
Oh, এটা বোধ হয় একটা হবে নাকি?
One, two, three. One, one, three. Two, one, three. So we know one at but we one at must have the identity of one. So we are like having five. Here the knowledge is ঠিক আছে এটা হচ্ছে 0.001 ঠিক আছে এটা এটা 109 পয়েন্ট সামথিং আছে ঠিক আছে অ্যাঙ্গেল y one style yeah zero. Atom double force is like top zero ঠিক আছে মাস হচ্ছে 1 और एलिमेंट হচ্ছে বন্ড প্যাটার্ন এস বেস চার্জ পোলারাইজেবিলিটি 1 ঠিক তারপরে হচ্ছে তোর ফোর্স সিস্টেম এসপিসি কি নাম্বার y
And it bonded to how many? People start the mornings. 0 1 0 1 0. We get that EA forms and submit it to our. Anybody left? We get EA form. Whoever is left. Submit it. No. I didn't. Oh yeah, we have to.